Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 9.8, which is power series. Alright, so first, let's define what a power series is. Obviously, it's some sort of series, but what kind? So definition of a power series. So let's put it this way. If x is a variable, and well, if x is a variable, then an infinite series of the form, so summation from n equals 0 to infinity of a sub n x to the n, right? In other words, in here what we're saying is a naught plus a sub 1 x plus a sub 2 x squared plus a sub 3 x to the third, so on and so forth, right? All the way through infinity. So if we have a series in that format, then that's called a power series. So that is called a power series. Right? Essentially because we've got powers of x there. All right, now, more generally, an infinite series of the following form the summation from x from n equals 0 to infinity of a sub n times x minus c to the n, right? In this case, it would be a naught plus a sub 1 times x minus c plus a sub 2 times x minus c squared, so on and so forth, right? A sub 3 x minus c cubed, whatever. So that's called a power series centered at c. So this is called a power series centered at c. All right, and here c is a constant, right? So now let's get some examples of power series. So something that looks like this: summation from 0 to infinity of x to the n over n factorial, right? And what would this be? Well, it would be plug in 0, x to the 0 over 0 factorial, that's 1. Plug in 1, x to the 1 over 1 factorial, that's just x. Plug in 2, x to the second over 2 factorial, x to the third over 3 factorial, and maybe I'll just write it as 3 factorial. 2 factorial, 3 factorial, x to the 4 over 4 factorial, so on and so forth, right? So that is a power series. This is centered at 0, right? So in general, if you have this version up here, then it's centered at 0, right? Let's look at another one. What if I have a series from n equals 0 to infinity of negative 1 to the n times x plus 1 to the n, right? This right here, what does that look like? That looks like 1 minus x plus 1 to the first power plus x plus 1 to the second power minus x plus 1 to the third power plus x plus 1 to the fourth power, so on and so forth, right? And in here, notice that this negative 1 to the n is the reason why we're alternating in sign. So this is essentially an alternating series that happens to also be a power series. Here, this is centered at, well, the form was x minus c, right? here we have x plus 1. I need to write that as a minus something. So this would be x minus negative 1. So our center there is negative 1. Let's write that a little better. There we go. So it's centered at c equals negative 1. All right. I'll get rid of that. Another example. Let's say we have decimation from n equals 1 to infinity of 1 over n times x minus 1 to the n. Right, well, what would this be? Well, this would be x minus 1. Well, we're starting at 1, right? So x minus 1 plus x minus 1 squared over 2 plus x minus 1 cubed over 3 plus x minus 1 to the 4th over 4, so on and so forth, right? All I'm doing here is plugging in values of n. And this here is centered at c equals just 1, right? Because it's x minus c. Here our c is 1, so c is equal to 1. All right. So we had already sort of discussed power series in the sense of we had worked with some of these, but we hadn't called them that. All right. Now let's discuss something called the radius and interval of convergence. Radius and interval of convergence. All right. So a power series in X can be viewed as a function of X. All right. So in other words, we can say that f of x is equal to some power series, right? Where the domain of f is the set of all x for which the power series converges. All right. So when we're talking about the radius and the interval of convergence, what we're essentially talking about here, what is the domain of the power series? And what does that mean? Well, we're looking for the domain of a power series. What that's saying is, what are all the possible values of x that we can plug into a power series so that we can still have a convergent sequence? A convergent series. All right. So let's see how we would do that. So let's use our theorem. Convergence of a power series. And this is what we're going to do. So for a power series centered at C, precisely one of the following is true. All right. So either the series converges only at C, so as a first scenario, the series converges only at C. So in here, what we're saying here is that the domain is just the center. That's C, wherever we're centered at, right? And here, so the domain we could write it into notation as from C to C, but that's kind of weird to say, right? Maybe we can also just say instead of domain is just the point C. I don't know. Anyway, in here, why does that have to be true, or why should that be true? Well, in general, a power series will definitely converge at its center, right? How come? Well, let's see. And I'll do this in blue here. So if I plug in the center here, I end up with the summation of a sub n times c minus c to the n. But then c minus c is 0. So I have 0 times a sub n. 0 times any value here for a sub n, because a sub n is a sequence there. 0 times that is still going to be 0. So what we're doing here is we just have the sum of 0, which is 0. And that's an actual value, so it's convergent, right? So that should make sense that a power series would always converge where it's centered at. So that's one of the possible scenarios, that it's only convergent at its center. The next scenario is that there exists a real number r greater than 0, such that the series converges converges absolutely for x minus c being less than r. What is that saying? So it converges for all the values within r distance of c. We'll get a visual of that. And diverges for the absolute value is x minus c being greater than r. Alright. So in here, what we're saying here is the domain would be something like this. Let's say here is our center. And what we're saying is all the values of x that are within some distance, right? Absolute value means distance, within some distance of c. Sorry, we're talking about this one. All the values of x that are within some distance of c are part of the domain. So let's say that this value right here, this distance is r, this distance is r. So that means that this value over here would be c plus r, this would be c minus r. We're saying the domain would be the entire thing there, all of those values in there. Right, that's the first part. Over here, diverges for everything outside of that. So we're saying it diverges for everything outside of that interval. Noticing here that this is an open interval. It's an open interval because of the strictly less than. We'll talk about what can happen at the endpoints later. But here what we're saying is that definitely inside everything there, it converges, and outside over here, it diverges. So in here we would say that the domain would be from negative, well, from c minus r to c plus r. All right. All right. And then the third scenario is the series converges absolutely for all x. Right. So in other words, here we're saying the domain is the entire real line, irrelevant of what the center is. So it would be in interval notation, the domain would be from negative infinity to positive infinity. So those are the three possible scenarios. In here, that number r is called the radius of convergence of the power series. All right. Now, I wanna casually mention something here. Now that we spoke about the radius, in here, in this first scenario, the radius would be equal to 0. In this third scenario, the radius would be equal to infinity. And the second scenario is really the one that we actually have a defined radius that is helpful, right? Well, saying helpful is weird. Let's say that it's an actual defined radius of more than just 0 or infinity. All right, so now, this interval in each one of these cases, that's called the interval of convergence, right? These intervals that I wrote here. So maybe I'll define that a little better. So the set of all values of x for which the power series converges is called the interval of convergence. And this one was a radius. All right, so let's actually get some examples in here. All right. So let's do some examples. All right. Let's the instructions here are just find the radius of convergence of the power series. So find the radius of convergence. And here we go. Example A. So we have here the series from n equals 0 to infinity of n factorial times x to the n. And recall, when we're saying here the radius of convergence, what we really mean is if we make this a function, what is its domain? All right, what is its domain so that the series overall converges? All right, well, we want this to converge, and it's a series. How are we going to actually do that? Well, we know that we want to somehow get that the absolute value of x minus c is less than r, so I can figure out its center and its radius. All right, well, what's its center here? Well, the center here is 0. How do I know that? Because we just here in our x, that's just x, right? So our center is 0. So x minus 0. All right, but now, how are we gonna get this out of here? So what we're gonna say here is, since we want this to converge, well, we've got a bunch of tests for convergence that we can manipulate. Specifically, we're gonna start with the ratio test. So we're gonna use the ratio test. All right, and remember that the ratio test was the limit as n goes to infinity of the absolute value of, I'm going to do it with u sub n plus 1 over u sub n is less than 1, right? And if it's less than 1, we knew that it converged. If it was greater than 1, it diverged. If it was equal to 1, then the ratio test was useless. But we're gonna do this. We're gonna apply the ratio test to this so that we can set it to be less than 1 and force it to converge. So, well, what does that give us? We have the limit as n goes to infinity of, well, what's u sub n in this case? U sub n is n factorial x to the n. And u sub n plus 1 would be n plus 1 factorial times n to x to the n plus 1. So we have here n plus 1 factorial times x to the n plus 1 over u sub n, which was n factorial times x to the n. At that point, well, we can rewrite this, right? Well, this actually values aren't doing anything, but this n plus 1 factorial is n plus 1 times n factorial. This x to the n plus 1 is really x to the n times x. And on the bottom here, this n factorial, and there's x to the n. So at this point, you see that a couple of things cancel out. N factorials, x to the n. So what do we get here? We get now that the limit as n goes to infinity of n plus 1 times x, right? So in here, well, what are we going to do? I'm going to put the x to the outside because it's not being affected by the limit. So we have x times the limit as n goes to infinity of n plus 1. Now, what is that? Well, as n goes to infinity, this piece right here gets huge. So for any fixed value of x, we would say that this is equal to infinity, right? And as you mentioned here, so maybe I'll make this a note here. For fixed values of x, x not equal to 0, because we're trying to stay slightly away from our center, right? So this is impossible to be less than 1, right? That's impossible. So because of that, the ratio test tells us that this series diverges for any value that's beyond 1. This means that's beyond 0. So thus, the ratio test shows the series diverges for any value of x that's bigger than 0. This tells us now that the series converges only at its center. All right. So this tells us now that the radius is equal to 0 because it only converged at its center. All right. All right. Next one. B. Let's say that we had the series from 0 to infinity of 5 to the n times x minus 4 to the n. All right. And well, let's see. Again, we're thinking of this as being a function, right? So that we can find its domain, because that's really what we're asking here. Find the domain of this function. And well, what are we going to do? Well, first, before we start, let's take a look at what our center is. Our center here is 4, right? Our center is 4. So what does that tell us now? Well, we need to do the ratio test, right? We need to do the ratio test. So let's do the ratio test. The limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. And we want that to be less than 1. All right, what does that give us? Limit as n goes to infinity of 5 to the n plus 1 times x minus 4 to the n over 5 to the n times x minus 4 to the n. Oh, sorry, n plus 1. There we go. Way better. At that point, well, let's rewrite this so we can see what cancels out. So we have the limit as n goes to infinity of the absolute value of 5 to the n times 5 times x minus 4 to the n times x minus 4. On the bottom, I just have 5 to the n and x minus 4 to the n. And from there, we see very clearly that these 5 to the n's cancel out, and x minus 4 to the n cancels out. So what are we left with? We're left with the limit as n goes to infinity of 5 times x minus 4, right? Well, look at that. We have no more n's in that limit, so this actually is just 5 times x minus 4. That's what it goes to. But we want that to be less than 1, right? We want that to be less than 1. Perhaps I'll write that on the next line. We want the absolute value of 5 times x minus 4 to be less than 1. But recall that we want this in the form of x minus c, absolute value of x minus c is less than r, right? And our center here is 4. So that means that we want x minus 4 is less than some r. That's what we want. So how do we do that with this? Well, we need to get rid of this 5 from here. So I'm going to divide both sides by 5. So I have the absolute value of x minus 4 is less than 1/5. So at this point, this tells us that the radius of convergence is so R is 1/5. All right, cool. Next one, example C. So let's say that we have the following: the series from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. All right, so let's notice something here. What is the center? The center is 0. What do we want? We want the absolute value of x minus c to be less than r, right? Because recall, when we're looking for the radius of convergence, what we're really saying here is, if we think of this as a function, what is its domain? And it's given by this, right? So in this case, well, since it's entered at 0, we really want x, the absolute value of x minus r, and we want to figure out what that r is. Okay, and how did we do that? Again, we use the ratio test. So we are going to do the limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. And what's u sub n and u sub n plus 1? Well, u sub n is just the series as written, right? And u sub n plus 1 would be -1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial. But now let's see. 2 times n is 2n. 2 times 1 is 2 plus 1 is 3. So we really have 2n plus 3 there. And here, for the same reasoning, we have 2n plus 3 factorial. All right. Now, what are we going to do? So we have the limit as n goes to infinity of u sub n plus 1. That was this big fraction over here. So we have -1 to the n plus 1 times x to the 2n plus 3 over 2n plus 3 factorial. And we have that divided by u sub n. But u sub n is a fraction, so instead of dividing by that fraction, I'm going to multiply it by its reciprocal. So we have 2n plus 1 factorial over -1 to the n times x to the 2n plus 1. Cool. Now, in here, since we're taking absolute values, those -1 to the n's don't affect us at all. The next thing, x to the 2n plus 3 over x to the 2n plus 1. We have the same base, different exponents. All we need to do there is subtract the exponents. So what does that give us? Well, we have the limit as n goes to infinity of the absolute value of x squared times, well, let's see, this 2n plus 3 factorial. We can rewrite this as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And why would I want that? Because I have a 2n plus 1 factorial in the numerator there. So what does this give us now? Well, everything else here canceled out, right? We already decided what happened with those x's. So we're left with a 2n plus 3 times 2n plus 2. All right. And now, let's see. In this limit, the x squared is not being affected by the limit, right? Because the limit is as n goes to infinity. So what we get now is the limit as n goes to infinity. Well, actually, we have an x squared outside of the limit because it's not affected by it. There we go. Of the absolute value of 1 over 2n plus 3 times 2n plus 2. This limit right here overall goes to 0. So what we really have here is x squared times 0, and we want that to be less than 1. Well, x squared times 0 less than 1. Well, for any fixed value of x squared times 0 is just 0, right? So when is 0 less than 1? Always. It's always less than 1, right? So in here what we're saying is that by the ratio test, the series is convergent for all x, which implies that our radius of convergence is infinity. So in other words, the domain for the function there was all real numbers, or is all real numbers. Now, we mentioned, or at least I mentioned something earlier. Well, maybe I'll scroll up to remind you. Here. When I was talking about this scenario here, I said, well, as long as we're less than r, it converges. If we're greater than r, it diverges. But what happens when this is equal to r? All right. So in other words, what's happening here at the actual point here and at the point over here? Because we already know what happens in between. We're asking about the endpoints of that interval. So let's figure that out. Let's see how that affects things. Endpoint convergence. All right. And in here, what we're really saying here is the interval of convergence. How do we find the entire interval of convergence? This is convergence somehow. All right. So recall the three scenarios that we just had. We had that the radius is 0. We had that the radius was infinity. So hold on. So here's our c. The radius is 0. Here's our c. The radius is infinity, so it goes throughout the entire real line. Right. The other scenario, the third scenario, is what if the radius is an actual value? So let's say that the radius is fixed and it's somewhere between 0 and infinity, but it's not 0 and it's not infinity. What does that scenario look like? Well, turns out we have a couple of different scenarios there. Here's our center. This is c minus r. This is at c plus r. So that's the first scenario. Actually, you know what? I'm going to change it. I'm going to make the open interval the first scenario. So that's the first scenario. Next scenario. The next scenario is that, well, maybe it converges for everything on the inside, but also at one endpoint. Next scenario. It converges on everything on the inside, but also at the other endpoint. And last scenario, it converges on everything on the inside, but also at both endpoints. So in here, these are all possibilities, right? And they're all different intervals of convergence. So to actually find which scenario you're in, well, all you really need to do is figure out, well, first the radius of convergence, and then what happens at the endpoint. So let's do a couple of examples. So find the interval of convergence. All right, so here we go. The series of x to the n over 7 to the n times n. And we're going from 1 to infinity. All right, and all right, again, to find the interval of convergence, we must first find the radius of convergence. And what did that mean? Well, the radius of convergence was equivalent to talking about finding the domain of this series as a function. Let's note here that the center is 0. Now, how do we find the radius of convergence? Well, we know that we have to have x minus c being less than r. That's what we want, right? in this case, our center is 0, so what we want is the absolute value of x to be less than r, right? That's what we really want. Now, how are we going to get that? Well, again, it is using the ratio test. And here, our u sub n is equal to x to the n over 7 to the n times n. Our u sub n plus 1 is x to the n plus 1 over 7 to the n over 7 to the n plus 1 times n plus 1. Cool. Now, let's actually apply the ratio test. And the ratio test says we take the limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. In this case, this means the limit as n goes to infinity of the absolute value of our u sub n plus 1, which is x to the n plus 1 over 7 to the n plus 1 times n plus 1 divided by u sub n. But u sub n is a fraction, so we can just say multiply by the reciprocal of that fraction. And at this point, well, let's see. We can rewrite some of these, right? Instead of x to the n plus 1, I can rewrite this as x to the n times x. Instead of 7 to the n plus 1, I can rewrite this as 7 to the n times 7. At that point, we see a few things cancel each other out. This 7 to the n cancels this one over here. This x to the n cancels that one over there. And what are we left with? At this point, we're left with, let's see, the limit as n goes to infinity. That's supposed to be an infinity symbol. There we go. That just goes to infinity of the absolute value of x times n over n plus 1. But now, this x is not being affected by our limit here, so we can rewrite this as x times the limit as n goes to infinity of n over n plus 1, right? And now, to figure out this limit, I'm going to multiply this by 1 over n over 1 over n, right? Because we're always allowed to multiply by 1. Remember that. So here we have the absolute value of x times the limit as n goes to infinity of the absolute value of, well, n times 1 over n is just 1. N times 1 over n is just 1. 1 times 1 over n is 1 over n. Since n is going to infinity, 1 over n goes to 0. So overall, this entire thing goes to 1. So what we really have here is that the absolute value of x, well, we have the absolute value of x times 1, right? And what is that we wanted? We wanted the absolute value of x to be less than r, right? Where this actually converges. Well, to use the ratio test so that our series converges, we have to have this being strictly less than 1, right? So, I mean, there's not really anything to do here. This is just the absolute value of x is less than 1. Hold on. Oh, no. Oh, no. I completely ignored that 7 there. Look at that. That's awful. This 7 should be down here. Should be down here. Well, actually, I can put it out over here. There we go. So let's fix this. Okay. And this is an x over 7 over here. Alright. Everything I said was still correct, with the exception of skipping that 7. So what do we have here? What we have here is the absolute value of x over 7, right? And then times 1, because that limit went to 1. Okay. Now, we want this to be less than 1. Well, we need to recall that what we wanted was that the absolute value of x to be less than some r. So we need the absolute value of x by itself here. So I'm going to multiply the 7 to both sides, giving me now that the absolute value of x is less than 7. There we go. That's how I knew I had made a mistake. I knew I needed to get a 7 in the answer. But anyway, in here, let's see. What we found here is that the radius of convergence is 7, right? So, and where are we centered at? We're centered at 0. So that implies now our interval of convergence. So this, our interval of convergence is, well, anywhere between -7 to 7. But the question is it parentheses? Is it bracket on one side? Is it bracket on the other side? Is it bracket overall? Which of those scenarios is it? All right, that's the next question. And again, in here, the way to do this, we gotta plug in those endpoints and see what happens. And we're gonna plug them into here. So maybe I'll copy this. All right. So we got test endpoints. Let's make this all one color. Test endpoints. All right, so first we're going to figure out, well, what is f of 7? F of 7 would be the summation from n equals 1 to infinity of 7 to the n, right? I'm plugging in x, 7 to the n over 7 to the n times n. And here these 7 to the n's cancel out, so I have the summation from n equals 1 to infinity of 1 over n. What does that series do? That series diverges, right? We can say it's a p series with p being equal to 1, or we can say it's a harmonic series. Either way, this diverges. So at 7, it's not a point of convergence, so we can't include 7. But what about negative 7? Well, what would that be? Well, that would be summation from n equals 1 to infinity of negative 7 to the n over 7 to the n times n. This ends up being the series from n equals 1 to infinity of, in here, this really reduces to just say negative 1 to the n over n. All right. Now this is an alternating series. This is an alternating series that I did at some point in the past. This is a convergence series. It converges. All right. And if you really wanted to show that it converges, you can say it's using the alternating series test. I'll let you do that as an exercise. But we have that it converges there. So this tells us now that we can include negative 7 in our interval of convergence, but we cannot include positive 7 in our interval. So this gives us the interval from negative 7 to 7, including negative 7, but not 7. And that would be our final answer. That's our interval of convergence. Cool. Let's do another one. E. Let's say that we have a series from n equals 0 to infinity of negative 1 to the n times x plus 1 to the n over 2 to the n, x plus 1 to the n. There we go. Right, and in here we're finding the interval of convergence, right? And again, essentially that meant we're looking for the domain of this function. Now, what is this centered at? This is centered at negative 1, right? Because it's x plus 1, and I had to write it as x minus c. What is it that we want to find first? We want to find the absolute value of x minus c being less than r. In this case, since our center is negative 1, what we want is x plus 1 to be less than r so that we can figure out our radius of convergence. Now, what are we going to do? Well, we need to figure out we need to do the ratio test to figure that out, right? So what's u sub n? Negative 1 to the n times x plus 1 to the n over 2 to the n. What's u sub n plus 1? That's negative 1 to the n plus 1 times x plus 1 to the n plus 1 over 2 to the n plus 1. What's the limit as n goes to infinity of the absolute value of negative 1 to the, well, let me write the generic thing. We're doing the ratio test. U sub n plus 1 over u sub n. Okay, there we go. So u sub n plus 1. So we have the limit as n goes to infinity of the absolute value of negative 1 to the n plus 1 times x plus 1 to the n plus 1 over 2 to the n plus 1 divided by u sub n. But u sub n is a fraction, so we can multiply by the reciprocal of that fraction. And at this point, let's rewrite some of these. We're taking the absolute value, right? So because we have absolute value, this negative 1 to the powers don't mean anything. Next thing, this x plus 1 to the n plus 1. I could write this as x plus 1 to the n times x plus 1. Cool. This 2 to the n plus 1, that's 2 to the n times 2. And now what cancels out? X plus 1 to the n with x plus 1 to the n. 2 to the n with 2 to the n. And what do we get now? Well, we get the limit as n goes to infinity. Well, what do we have left? X plus 1 over, this 2. Can't forget that 2. Over 2. Right? And, well, since we're taking the limit as n goes to infinity, there's no more n's here, so we can just say this is simply the absolute value of x plus 1 over 2. But now, we want this to be less than 1. And why do we want it to be less than 1? Because, well, in the ratio test, that's where things converged, right? Where that limit was less than 1. So the next thing is, well, we need absolute value x plus 1 to be less than r. We need to put it into that format. So in here, what we have is x plus 1 is less than, multiply the 2 to both sides, it is less than 2. So that tells me now that my radius of convergence is 2. And, well, what was my center? My center was -1, right? So our center was -1. So what this tells us now is that, well, if -1 is our center and our radius is 2, -1 minus 2 is going to be -3. -1 plus 2 is +1. So that means we're working with either that set, or this set, or this set, or this set, right? But it's going from -3 to 1, right? So what we need to do here is check the endpoints. And how are we going to do that? We're going to plug them into here. So let's copy that. So endpoints. No, let's put that a little higher. So what were the endpoints? The endpoints were -3 and 1. So let's figure out what happens to at -3. So f of -3 would be the series from n equals 0 to infinity of -1 to the n times -3 plus 1. -3 plus 1 is -2. So I have -2 to the n over 2 to the n. But notice here that all these are to the power of n. So what we can really say here is we have the series from 0 to infinity of everything to the n. And what is everything? -1 times -2 over 2. But -1 times -2 is just 2. And 2 over 2 is just 1. So what does that give us? We have the series from n equals 0 to infinity of 1 to the n. Well, 1 to the n is just 1. So we have the series of 1. So we're adding 1 over and 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 over again. That goes to infinity. That's divergent. So we cannot include that -3. Alright, so let's see what happens at 1. So plug in 1. So we have the series from n equals 0 to infinity of -1 to the n times 1 to the n over 2 to the n. Well, this 1 to the n isn't doing anything. Hold on. X plus 1 to the n. Ooh, so it's 1 plus 1 to the n. So 1 plus 1 is 2. 2 to the n. That changes. Okay, 2 to the n cancels out. Nice. So what does this give us? This gives us the series from n equals 0 to infinity of -1 to the n. But that's also divergent. Why is it divergent? Because, well, think about what's happening here. This is saying 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on and so forth, forever and ever and ever, right? So this is also divergent. Remember, divergent just meant it doesn't go to any specific value, right? And here, since this is alternating between adding 1 and subtracting 1, it's not going to go into any specific value because we're doing that forever and ever and ever. All right, so we just found that we couldn't include either of the endpoints. So that tells us that our interval of convergence is from -3 to +1, not including either of the endpoints. Cool. So that was E. F. Let's say we had the series from n equals 1 to infinity of x to the n over n squared. All right. So again, let's note a few things. Well, we're looking for the interval of convergence, right? In here, our center is 0. We want to first find the radius of convergence, and for that, we need to find the absolute value of x minus c to be less than r. In this case, since c is 0, we have the absolute value of x being less than r. Cool. We want to use the ratio test, so we need to figure out u sub n. That's x to the n over n squared. And we need u sub n plus 1. That's x to the n plus 1 over n plus 1 squared. Cool. Now, let's do the ratio test. The limit as n goes to infinity of the absolute value of u sub n plus 1 divided by u sub n. And that means we're going to take the limit as n goes to infinity of the absolute value of u sub n plus 1, which was x to the n plus 1 over n plus 1 squared, times, well, technically divided by u sub n, but u sub n is a fraction, so I'm going to multiply it by the reciprocal. So we have n squared over x to the n. At that point, well, what can we say? X to the n plus 1 is really just x to the n times x. And, well, that cancels these two out. That's pretty much all that cancels though, right? And in here, let's see. This x is not being affected by the limit, so we can take it out of the limit. So I have the absolute value of x times the limit as n goes to infinity of the absolute value of n squared over n plus 1 squared. Let's see what we can do there. Well, I have both the numerator and the denominator being squared, right? So what I can do here is rewrite it as the limit as n goes to infinity of n over n plus 1 squared, right? And then we know that we're allowed to multiply by 1, because multiplying by 1 doesn't change anything at any time. So I'm going to multiply by 1 here by doing 1 over n over 1 over n here on the inside, all right? And how does that helpful? Because, well, now we get the absolute value of x times the limit as n goes to infinity of the absolute value of n times 1 over n is just 1. N times 1 over n is just 1. 1 times 1 over n is 1 over n. We have that squared. Well, let's see. 1 over n goes to 0. 1 over 1 plus 0 goes to 1. 1 squared goes to 1. So we have the limit as n goes to infinity just went to 1. So what we really have here is just the absolute value of x, right? Cool. So in here, well, what is that going to do? What we need to do here is, well, what this tells us is that the absolute value of x is, we want it to be less than 1, right? We want it to be less than 1 because we were using the ratio test, and for the ratio test to converge, it has to be less than 1. So in here, well, this tells us that the radius is 1, right? We already have in the format that we wanted it in. This is the format that we wanted it in. So the radius is just 1. We're centered at 0. So this tells us that we're either working between -1 and 1, not including the endpoints, or including one endpoint, or including the other endpoint, or including both endpoints, right? So what are we going to do there? Well, check the endpoints. And to check the endpoints, let me first copy this piece over here. And I guess I should have said here, just like before, that f of x was that, right? Because we were looking for the domain of that. All right, cool. So we're going to test the endpoints. And since what were the endpoints? -1 and 1. Okay. So we're plugging in -1, which gives us the series from n equals 1 to infinity of -1 to the n over n squared. This right here, I'll let you do the actual test this here for this, but this is convergent by alternating series, right? So that's convergent at -1. Again, I'll let you figure out the test on your own as an exercise. If I plug in 1, what is this series? The series becomes a series from 1 to infinity of 1 to the n over n squared. But 1 to the n is just 1, so I have 1 over n squared. That is also convergent by p series, right, where p here is equal to 2. So in this case, we had that it is convergent for both endpoints, right? So this tells us now that the interval of convergence is from -1 to 1. All right, cool. Now let's talk about some properties of these power series. All right, so theorem. Properties of functions defined by power series. So, all right, let's see here. If the function f of x is equal to a power series, right? And here recall what this power series really is. When I plug in 0, that's a naught. When I plug in 1, that's a times x, a sub 1 times x minus c to the 1. Then I plug in 2, plug in 3, so on and so forth, right? So if that function has a radius of convergence r, where r is greater than 0, then on the interval on the interval c minus r to c plus r, in other words, in its interval of convergence, and well, actually, in its interval of convergence without ever including the endpoints. Why? Because we're going to say here that f is differentiable and therefore continuous, right? There was a theorem that said that if a function is differentiable, it is continuous, and therefore continuous on that interval, right? Moreover, the derivative of f, both the derivative and the antiderivative are as follows. Are as follows. So f prime of x would be the series from n equals 1 to infinity of n times a sub n times x minus c to the n. All right. Notice that I'm taking the derivative of this piece. Bring the exponent down to the front. So, n minus 1. Subtract the exponent minus 1. Right? So that would be our derivative. In here, well, what would happen when I plug in n equals 1? Well, when I plug in n equals 1, I end up with a sub 1 plus a sub 2 times x minus c. Sorry, 2 times x sub 2 times x minus c, right? Here n is equal to 2. N is equal to 3. 3 times a sub 3 times x minus c to the second, right? 3 minus 1 is 2. Plus 4 times a sub 3 times x minus c to the third, so on and so forth. All right, that would be the derivative. I want you to note something here, though, and it's a very, very subtle thing. I wrote n equals 1 here, and I wrote n equals 0 here. All right. Why would that change? Why do we have a different index? Well, the reason for the different index is that here, this a naught, it is a constant, right? And because it is a constant, when I go to take the derivative of it, it goes away. So it's no longer there. All right. So in here, this is one thing to keep in mind. If your power series has a constant term, you're going to lose a term. But if it does not have a constant term, then you're not going to lose a term. But in this case, since I'm doing it more generically, where that constant term is possible, I am losing a term here. All right. But again, if your power series did not have a constant term, then you would not be losing any terms there. All right. So that's the derivative. The antiderivative. So the antiderivative of f of x dx would be c plus the series from n equals 0 to infinity of a sub n times x minus c to the n plus 1, all of this over n plus 1, right? And in here, what are we saying? We're saying c plus a naught times x minus c plus a sub 1 times x minus c squared plus, oh, hold on. We're supposed to be doing it over n plus 1, right? And here n is 0, and here n is 1, so this is over 2. A sub 2 times x minus c to the second. Hold on. Add 1 to the exponent. To the third. And then this is over 3. So on and so forth, right? But notice here that I have this extra c. What is that? Why is that c there? Because, well, we're doing an indefinite integral, right? The antiderivative, and the antiderivative should be in a generic form, where you write the constant of integration there. All right. And here, notice I went still from 0 to infinity as the original one did, because we don't lose terms when we're doing the antiderivative. If anything, we gain terms. All right. But in this actual piece, from here on, there's not going to be any new terms being added, or removed. So we just stick with the index as it was. Now, in here, it's worth it to say the following things. So the radius of convergence of either of these. So, all right. So in here, this function has some sort of radius of convergence, right? And the radius of convergence implies some sort of interval. For the derivative and for the antiderivative, the radius of convergence doesn't change. What might change is the interval. So what are we saying here? So the radius of convergence of the series obtained by differentiating or anti-differentiating, or anti-differentiating a power series is the same as that of the original power series. As that of the original power series. All right. The interval of convergence, however, might differ at the endpoints. So the interval of convergence of the series obtained by differentiating or anti-differentiating a power series may differ at the endpoints. So what do we mean there? Well, what we're saying here is, since the radius of convergence is going to be the same, all we really need to figure out is, for the interval of convergence, what is happening at the endpoints. So let's do an example here. G. So let f of x be equal to the series from n equals 1 to infinity of x to the n over 7 to the n times n, right? And in here, what is that? Let's plug in a couple of terms to see. Well, I can't start at 0, right? Because I can't plug in 0 into the denominator. So let's plug in a couple of points to see if we have any constant terms. So I have x over 7, right? When I plug in 1, plus x squared over 49 times 2, 98, plus x cubed over, I'm going to write it as 7 to the third times 3. All right, I have no idea what that is. But whatever that is, that's what it becomes. So on and so forth. But notice that we don't have any constant terms. So I'm just writing that there just so that I can keep in mind that when I take the derivative or the antiderivative, I know that we're not going to lose any terms here. All right, so what we're going to do here is we're going to find the interval of convergence for f of x. Let's rewrite that better. F of x for f prime of x and for and for the antiderivative of f of x. All right. So let's see. For one, to find the interval of convergence there, well, first I want to show you something. Here in example D, that's exactly the same series that I used. So we already know the interval of convergence. The interval of convergence here, well, where is it? There it is. It's from -7 to 7, including -7, but not 7. So here I'm going to say, well, see example D to figure out how we found this, but the interval of convergence we just said was from -7 to 7, not including 7, but we are including -7. All right, very exciting stuff. Now, that's for the first one. For the second one, well, we're going to figure out f prime of x. So what is f prime of x? F prime of x would be the derivative of this thing with respect to x. Well, that would be the series from n equals 1 to infinity. And again, since we didn't have any constant terms, I'm not losing anything here on the index, right? And I'm going to have n times x to the n minus 1 over 7 to the n times n. At that point, you see clearly that that n cancels out, right? So that cancels out. Now what we have here is just really the series from n equals 1 to infinity of x to the n minus 1 over 7 to the n, right? And well, we already know what the interval of convergence should be, somewhere between -7 and 7, but we don't know whether or not to include the endpoints. So what we're going to do, plug in the endpoints. So what is the endpoint here? So let's figure out the left endpoint, -7. Well, that's going to give me the series from n equals 1 to infinity of -7 to the n minus 1 over 7 to the n. And what is that going to do? Well, let's see. -7 to the n minus 1 really means -7 to the n. I don't want to write that again. -7 to the n times -7 to the -1. And we have this over 7 to the n, right? And at that point, well, these two right here, that reduces to be just -1 to the n, right? So we have here, I will write this as the series from n equals 1 to infinity of -1 to the n over -7, right? -7 to the -1 would just be -7 there. And since that -7 is not being affected at all by the index here, we have -1/7 times the series from n equals 1 to infinity of -1 to the n. But this right here is divergent. So that means that we can't use that -7 for this piece, right? So I'm talking about this series right here, -1 to the n, that's divergent. And now let's figure out what happens at the other endpoint, f prime of +7. Well, we're going to get the series as from 1 to infinity of +7 to the n minus 1 over 7 to the n. And here, well, what is this going to give us? This is going to give us the series from n equals 1 to infinity. This is really 7 saying 7 to the n times 7 to the -1 over 7 to the n. These 7's to the n's cancel out, so I have the series of 1/7. So I'm going to put that 1/7 on the outside. So 1/7 times the summation from n equals 1 to infinity of 1. This also diverges. That's a series that's just adding 1 forever. That's divergent. And this tells us that, well, it was divergent at both endpoints. So the interval of convergence for f prime is from -7 to 7, not including either endpoint. Cool. But we also asked about the interval of convergence for the antiderivative. So let's figure that out. So first, let's figure out the antiderivative of f of x dx. Well, in this case, it's going to be c plus, well, we need to add 1 to the exponent and divide by the new exponent. Where's our c? Oh, I went too far up. Add 1 to the exponent, divide by the new exponent, right? So in here, we're going to have the series of add 1 to the exponent, divide by the new exponent. And we're still going from 1 to infinity, right? And now, at this point, well, we're trying to figure out what happens when we plug in 7. So what we're saying here is the antiderivative of, well, let's plug in -7. What is that going to give us? Here we're going to say that this is c plus the series from n equals 1. You know what? I don't like that notation. Let's leave that notation alone. Let's just say for x equals 7, this is what's happening. All right. C plus the series from 1 to infinity of 7 to the n plus 1 over 7 to the n times n plus 1. Cool. What is this going to give us? This is going to give us c plus the series from n equals 1 to infinity. 7 to the n plus 1 over 7 to the n is just 7. On the bottom, I have n times n plus 1. And, well, what is that going to do? That is going to converge. I will tell you that right now. This converges. How do I know that it converges? Well, you can do a direct comparison test. Direct comparison with the series of 1 over n squared. Alright? So I'll leave that for you to figure out how that converges using that. But it does converge. And alright, so it converges at x equals 7. But now what happens at x equals -7? Well, when we plug in -7, we get the following. So we get c plus the series from n equals 1 to infinity of -7 to the n plus 1 over 7 to the n times n plus 1. At this point, we say, well, -7 to the n plus 1, and then, well, what does that become? Well, let's write it this way. This is really saying -7 to the n times -7. And here, -7 to the n and 7 to the n just become -1 to the n. So what do we have here? Well, let's write it this way. C plus the series, perhaps I'll write this a little bit lower. C plus the series from n equals 1 to infinity of -1 to the n times -7 over n times n plus 1. Alright, now this is an alternating series. Alright, and I'll tell you right now that this alternating series converges. So it converges by alternating series. Again, I'll let you work out as an exercise this how this converges using the alternating series, but it does converge. So what we have now, so the interval of convergence, so the interval of convergence is from -7 to 7. And that is the end of 9.8. Cool. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.